5.6. Second law aspects of power cycles interacting with two reservoirs. A power cycle or a heat engine and a heat pump and refrigerators interact with two different thermal reservoirs. A power cycle is a device to produce work continuously. It receives heat from a high temperature reservoir and converts part of the thermal energy to work, and it rejects the remaining thermal energy to a low temperature reservoir, such as the atmosphere or lake. Let's see a schematic of a power cycle. This is a power cycle between the two reservoirs. We have two reservoirs, hot reservoir and cold reservoir. QH is the heat transfer between the cyclic system and the high temperature reservoir, or simply it is the heat input to the cyclic system. QC is the heat transfer between the cyclic system and the low temperature reservoir, or simply heat output from the cyclic system. The work produced by the system is QH minus QC. The performance of a power cycle is expressed as thermal efficiency. Efficiency of a device is defined as the ratio of the desired output divided by required input. So the thermal efficiency of a power cycle is defined as work divided by the heat input. So we use the symbol eta to denote thermal efficiency of a power cycle. As shown in the schematic diagram, the heat input is QH. The work output is the difference between the heat transfer in and heat transfer out. QH minus QC. QH is always less than QC, so the thermal efficiency of a power cycle is always less than 1. The maximum theoretical thermal efficiency of a thermodynamic cycle can be evaluated with reference to the following two Carnot-Conorellis. The first Carnot-Conorellis. The thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible cycle when each operates between the same two thermal reservoirs. So let's think about the high temperature reservoir. Temperature at TH, and low temperature reservoir, temperature TL. And consider a power cycle operating between the two reservoirs. This is power cycle. And this is reversible power cycle. Heat flow from the higher temperature reservoir and it produces work, and the remaining heat will be rejected to the low temperature reservoir. Consider another power cycles between the same two reservoirs. But this time, this power cycle is irreversible. The same amount of heat will be supplied to the power cycle. It will produce work, and the remaining heat will be dumped to the low temperature reservoir. And compare the work by reversible power cycles and irreversible power cycle. So work produced by the reversible power cycle is greater than the work by the irreversible power cycle. We can also say efficiency of a reversible power cycle is greater than efficiency of a irreversible power cycle. The second Carnot corollary. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. So this time consider two reversible power cycles, but they have different designs. As long as they have the same two reservoirs and they are reversible cycles, they have the same thermal efficiency. So efficiencies of both cycles are the same as long as they have the same two reservoirs and they are reversible.